Okay, so now it's time to talk about the fuel system, specifically about carburation. We're going to have a whole class on how the fuel gets onto the plane and then moves around the plane into the engine. Today, we're just going to talk about just carburation, and we're not going to we'll get a little bit into fuel injection, but not into fuel tanks, fuel lines, and all that kind of thing. Just the process of mixing air with fuel for the sake of combustion. So let's just establish a theory. It's a baseline theory of like fuel to air mixture, what makes it right, what makes it wrong, and then how does it go through the process via a carburetor or some sort of carburation like process in order to make it actually be combustible. All right, now before we really get going on the particulars of carburetors and carburation, we really need to understand fuel mixture, what it is, and what can happen if we get it wrong. Now, let's just start on this chart and work our way from left to right. What is a fuel-air ratio? Well, there is a proper mixture, just like if you were baking a cake or mixing paint or anything else, of between fuel and air to get the right outcome. If you have too much fuel, that leads to a certain set of circumstances. Worst case scenario, it just doesn't light off at all because it's just basically just a big jug of fuel with an electrical spark going and not enough air to combust it. Or on the other end of the spectrum, where it's way too lean and weak, you just won't have enough fuel in there to light. Just like if I lit a match in the middle of this office right now where I'm recording this thing, nothing would happen because there's not enough fuel in the air to cause it to combust. So we have to have that Aristotelian mean between fuel and air, the right mixture to make it go off, just right. Now, what does that look like? Now, if when we have too much air, that means that the fuel has been leaned out, and that can lead to a bunch of circumstances. Even if you can still get combustion to happen, if the fuel is the mixture is too lean, it can still damage the engine. Same thing as if you have too much fuel, it's too rich. It's on the right-hand side of the spectrum here. Now, this air to fuel ratio here, this graphic, kind of gives you some idea of like lean would be 20 parts air, 1 part fuel, whereas a rich mixture would be 12 parts air, 1 part fuel. Now, I wouldn't take that to the bank, but it just kind of gives you an idea. Kind of a visual of what that could potentially look like. Now, your carburetor, your fuel injection system, or whatever, its whole purpose is to make sure that you have fuel that's not only leaned correctly, but also atomized. Now, what is atomized? You can think of atomization as simply just the spraying of fuel so that it's this fine mist, all right? Now, anything to do with fire largely will depend on the surface area of the thing that you're trying to burn, the combustibility of it. Now, if you increase the surface area and the combustibility stays stagnant, well, then you're going to have more surface to burn because you're going to have a bigger surface area with more interaction with the oxygen molecules in the air. So, therefore, if you have like a piece of paper and you wad it all up and you go to burn it, it's going to go really, really slow because it's having to like work its way through all those creases and folds and everything. However, you lay it flat, the same piece of paper, and you light it, it's going to go really, really fast because it's a lot more efficient. All right. Well, atomization of fuel is simply the same thing. Is that if you were to spray the fuel, then those little bitty molecules that are sprayed out in that atomized process, that little mist, it has 360 degrees around these very, very small bits of fuel, so that way it interacts with the oxygen in the most efficient manner possible. So therefore, it'll fire off more reliably. Now, you could have a situation where, say, like a cold engine. One of the reasons a cold engine will start and sputter and things like that is because it's so cold that it really disrupts the atomization of that fuel and causes it to kind of glob together and not really want to spray appropriately, and you end up having a poor atomization pattern, so therefore it doesn't want to fire off as efficiently as possible. But once it gets warmed up, then the fuel wants to kind of expand. It lends itself to atomization, and then it's good to go. And there's other reasons too for a rough running engine whenever it's cold, but that's one of the things that could potentially happen. Now, let's look at the Okay, so what happens if a mixture is too lean? Well, what's going to happen is that you're going to miss a cycle. So, like, it's going to not have enough gas in there to combust, and it's going to be firing, and it's not going to combust and light off, and then the engine will go through the entire cycle again, but without the pressure to push the air out. With the fuel in there, it's going to want to stick to the sidewalls of the chamber. But then whenever the next cycle happens, it's going to get another puff of fuel into it, and now you have too much fuel in there. And then as that piston comes up, one of the things that can potentially happen is called detonation. That's where instead of having a nice clean burn, effectively you just have a bomb and it blows up. And you can see here from these Lycoming pictures of what the effects of detonation can be. You see the whole sidewall, the piston is just blown up, burnt down the side. The valve is totally unseated, and it's nothing good. It comes from an engine going through detonation. Now, if the engine is progressively or always running too lean, you're going to end up having like high CHT, so cylinder head temperatures, high EGTs, exhaust gas temperatures, and you're also going to not make near the amount of power that you would want, simply because it's being starved of fuel. Like if I were to say, like limit you to like 400 calories a day, and then make you run marathons every day, you're just eventually just not going to be able to do it anymore. The math between calories out and calories in will eventually just you'll go through a lot of weight loss, and then eventually you just won't be able to do anything anymore. So this is what can potentially happen if it's too lean for too long. It just won't run and won't run, and then the worst case scenario is you eventually end up with detonation. Okay, so what happens if it's too rich? Too rich would just simply mean that you are not burning all of the fuel that's available. I mean, the engine's only going to burn for so long. This cycle only goes for so long, and there's only so much air in the chamber, so it could burn, and then you're going to have a bunch of just leftover fuel that just wasn't combusted entirely. And just like with any other fire, leftover material turns into soot, ash, or residue of some variety. Well, whenever it's running too rich, a lot of that soot ends up on your spark plug, just like you see here. So you can see on the right, running spark plug on the right hand side, and then a super lean one on the left hand side, and in the middle is this overly rich engine that leaves a bunch of trash on the spark plug. Now, whenever we get to do engine services, we're going to clean these spark plugs, and you'll be able to see kind of the progression from a rich or even just normal usage spark plug to what the spark plug is supposed to look like. And it's always amazed me how dirty they end up getting, even though they're inside a cylinder of an engine. So you can imagine that if there's just a lot of extra trash in there, you could potentially really start to disrupt the use or the proper working order of the spark plug, so it stops it from letting the engine fire. Okay, so what is the optimum fuel mixture for our engine? Well, here we have a graphic out of the 8083 that will kind of give you an idea of how much your fuel should be set at, where it should be lean or rich at different stages of the game. So we're going to start on the left hand side, and we're going to work our way across. Now, when you crank an aircraft, one of the first things you're going to do is you're going to put the mixture into the full rich position, and that's what we see on the far left hand side. That it's rich, you're giving it as much fuel as you can whenever it is it's just been cranked. Now, typically you're going to do this graphic really doesn't do it justice per se, but on the right hand side where it says takeoff, you're also going to be full rich. Now, I imagine what they're trying to say is that, like, since the airflow has increased since you're taking off and it's running, the extra air is going to help lean that mixture out, and that's true. But for the sake of our purposes, you're going to put it into the full rich position. and then you're going to firewall it, and then it's going to blast off with the most amount of fuel available to that engine. And there's the air going through it, through the cylinders, because it's now at a higher RPM, is going to help lean that mixture off. Now, whenever you get to your cruise altitude, one of the things that you'll do is lean that mixture back a little bit, and you'll see the RPMs increase on the on your tachometer. You'll see that the higher up you go, the lower your RPMs start to get, and then you'll pull the mixture back, and then all of a sudden the RPMs will come back up. Now, why do you think that is? Well, I'll tell you, since we're not in class and we're on a video. What's happening is that as the air gets thinner, the higher up you go, you want to keep that 1-to-1 ratio, that perfect mixture ratio, so that way you make the maximum amount of power out of your engine. The only way to really do that is to reduce the amount of fuel going into the engine, because there's less air in the engine. So I always tell people, like, there's a 1-to-1 fuel mixture that you need to maintain, and so like what you're doing, since there's less air, you need to meter the fuel so that there's less fuel. Okay, so let's think through this, right? Let's say you have the ground right there, and you have your little airplane that's on the ground. There's wings and a propeller, whatever, all right? On the ground here, we have, all of this air. And we have all the atmosphere that's above it that's starting to push down on it. And because it's pushing down, and all that air is super, super duper compressed. It's at 0 feet sea level, and it is the densest air that you're going to get on this whole flight. Well, now as we go to take off, we're going to go up, all right? So we fly up, and we're at, we'll say, 15,000 feet, all right? So we're at 15,000 feet. Now, you think about this, right? The atmosphere has decreased in volume about 15,000 feet, whatever that math works out to be. All right, so all of that weight that had compressed that air down now it's not compressing the air down as much, because there's all this space that we've eliminated from what's above us. All right, so instead of having in this kind of pattern here, this like super compressed air, we only get like. There's two things to take away. One is that there's simply less of it. Notice that there's 6 particles of air here, but there's 9 particles of air down there. And the other thing is, look at the big gap that's between. They're spread all apart because they're not being as compressed as much. And then whenever we go to land, we're going to come back down, and we're going to be back in this configuration over here. We'll have the same air density that's happening there, provided we come down at the same place. And you could always land up at a mountaintop, and then it stops the process about halfway through, but that's neither here nor there. So let's think about this. Now, if we wanted a 1-to-1 fuel to air ratio, we would need to have a particle of fuel for every particle of air down here, right? So our fuel down here would look like this. So this, call that fuel and call that air, okay? But whenever we get up top, when we get to our top of climb at 15,000, if we maintain this same construct right here, the same amount of fuel going into the cylinder, instead of having 6, we would have 9 particles of fuel for the 6 particles of air. So call that A, call it fuel, all right? So what we have to do is we have to pull some of that fuel out of the mixture, and we do that by simply just, erasing some of that fuel, so that way we have that 1-to-1 ratio. So just like we had, 9 particles of fuel for every 9 particles of air down here, we have 9 particles or 6 particles of fuel up here for 6 particles of air. If we leave it on this ground setting, you'll see that the power will just slowly start to just give away as you go up. And so in order to maximize that power and get the most out of your engine, you want to set that just right. Now, you could be in a situation where you leave it for a long period of time, and eventually you're going to cause the spark plug to foul, and then the engine's going to start running rough, and you're going to be like, what's going on? And that's what's happening. So that is what we call leaning the mixture, all right, and maintaining a proper fuel to air ratio. Now, The device that does that, or helps us do that, is the carburetor. In the aircraft, you're going to have a little red knob that you'll push in and push out, and that is going to change the amount of fuel going into the carburetor that gets mixed in with the air that then goes into your cylinder. So let's talk about those. Okay, the heart of every carburetor is essentially the venturi. Now, what the venturi is, if you remember back from General, is simply a neck-down tube, for the lack of better terms. And what that's doing is it's taking the same volume of air that's moving it at a certain velocity, and it's causing it to get squeezed and therefore go faster. As it goes faster, it will exit the venturi and start to expand. So if you look at this graphic here, there's three sets of dials. There's like one little stem that breaks off into two different or gauges, for lack of a better term. You'll notice that the velocity and the pressure is straight up and down. It's say we'll put that 12 o'clock position on the left hand set of gauges. Then whenever it enters in the venturi goes faster. And then because because that air goes so much faster, the pressure starts to drop. As the pressure drops, and so does the temperature, by the way, which will come into carb heat here in a little bit. The venturi goes forward, and then it expands back to being normal on the other side. Now, the carburetor is going to use that pressure drop to help pull the fuel out of the bowl and then put it into the air to cause it to run. So if you kind of think about this, is that, like, let's say the fuel cell is on the left hand side. It's just a big tank, and this thing is just directly attached to it. And then on say it's the outside air, right? And then the fuel cell basically pipes down into the venturi. And on the right hand side is the cylinder that, as that cylinder comes down and it sucks that air. It's going to suck air in, and then that low pressure is going to pull fuel from the tank into that venturi, mix it together in a little spray pattern, and then off it goes into the cylinder for the next compression and ignition stages of it all. And that is, at the heart of it, all a carburetor really is. Everything else you see on there is just to facilitate that whole interaction in the way that we need it facilitated at the time that we need it facilitated. Okay, so this is a carburetor. So it looks like. So generally speaking, it would sit something like that on the bottom of an engine, and most of the time on aircraft they're going to be on the bottom. Sometimes they get located in different places, but generally speaking, on GA aircraft you're going to see them located on the bottom, and you can very clearly see it because you have a hose that will come from the filter and then up into where the carburetor is at. On the Rotax engines, they're on top, and it's the same thing. You get the filter, here's the hose, boom, into the carburetor. Just kind of orient you to the carburetor itself. Here's where your fuel line will come into it. This is the throttle arm, and you'll notice the throttle arm turns the throttle plate. Now, this is like what the plate looks like whenever it's wide open. Notice that the plate doesn't obstruct. You can see my finger through that thing, and it just lets air and fuel come through there. If you wanted to shut off the engine, that's what happens. Nothing can get by. And the only thing that's going to happen is the idle, which it comes from this little bitty inlet right there. Idle fuel will come in there. There's an idle needle that regulates how much fuel can come through there to just keep the engine running. So whenever they say adjust the idle on something, they're talking about adjusting the needle to make sure that just enough gas gets in there and it doesn't idle too high and also doesn't idle too low. It should be a nice, very low RPM, steady, smooth, rhythm. So like you should be able to back the idle off a little bit and feel it will start to miss and get really, really rough, and then increase that idle just a little bit and it'll start to plane out and be nice and smooth. But that's the idle, that's what they're talking about. This is also the venturi, and you'll see like there's a venturi body on the inside of it that causes it to neck down. This is called the bowl. So the fuel will effectively like sit there. And so I guess on this in particular a carburetor, the fuel will sit right there, and then you'll have the updraft that'll pull it into wherever it's going. And yeah, so that's kind of like your throttle, your carburetor body, carburetor bowl. There's a lot of nuance to it and a lot of detail to them. But on the whole, it's very, very basic. You have Venturi and the idle, throttle plate, throttle arm, and then that's pretty much what there's to it. Now, as we break these things apart, there'll be a float, but we're going to get into that when we start talking about like float carburetors, pressure carburetors, so on and so forth. But really, they're not super duper complicated. They're actually pretty ingenious when you stop and think about the era in which these things were developed and how they were developed, and a lot of the I guess back and forth that went into it to make sure that it worked really well. So that is actually fairly impressive. But honestly, they're not like state of the art, super complicated things. You need to have a really good eye for detail with them, though, because a little bit goes a long way with these things, and little things can completely throw it off. That's why, like carb ice is a big deal with them. Like if you get ice on that throttle plate, it'll start to jam up that venturi, and nothing can get through there. So you'll have to apply carb heat to melt the ice, and then you'll see the engine RPMs continue to go down as the throttle or as the fuel mixture gets impregnated with water. But then as it cleans it all up, it'll start to come back up again. So yeah. That's it. The only other kind of thing that's really interesting about this is they all have a fuel screen in it. So there's a little screen filter. So you can see that the fuel enters on this side, and then there's a screen that marries up. There's that hole right there, and then the fuel comes out this little mesh, and that keeps any trash that might be floating around in your fuel tank and then entering through the carburetor from getting into the carburetor bowl and venturi and so on and so forth. Yeah, but that's carburetor basics right then and there. Okay, so the grandfather of all carburation appliances is the float type carburetor. Very, very common, especially the older you get, the more float type carburetors you're going to actually start to see. So let's build our understanding on what a float type carburetor is, why it works the way that it works, and some of the things that we need to be aware of if we're doing maintenance on them. Okay, so this is kind of a cutaway of what a float type carburetor would look like on the inside. Now this is kind of simplistic, however, it's really useful just to kind of get an idea of like what you're looking at there. We're going to start on the left-hand side because we've already kind of gone over that. You can see that if you just follow the graphic from top to bottom, that's the air-fuel mixture. That's what the product of the carburetor. That's what it's going to produce. The throttle valve body right there, that's the throttle plate that we looked at a second ago as it opened and closed via the throttle arm. And then the venturi is really where the magic happens in a carburetor. That's where it necks down, it squeezes, it drops the pressure. And then you have the discharge nozzle. Now, the discharge nozzle is connected to the float bowl off to the right side there. Now, the float bowl it can confuse some people and seemed like this mystical land of magic that's where the carburation happens, but it's not necessarily the case. It's really pretty simple. If you're familiar with like a livestock tank where the cows will drink the water and then there's a float that will fall down as it goes down, and it opens up a port that allows water to come back in to fill the float or fill the bowl back up until the float closes the valve again. That's essentially all that you have, and that allows for the metering of the fuel going into the carburetor to be steady and constant. So if there's a lot of fuel that's being consumed, then that's going to drop the bowl, which then drops the float, which takes in more fuel. If it's just idling, it's not taking a whole lot, the bowl will generally stay pretty full, and that'll keep the fuel from flooding the engine and causing all kinds of problems there. Now, the way that it does that is through the float itself, which isn't labeled here, but it's a little green ball that's just floating, and all it does is goes up and down, floats up and down. It's pretty simple, pretty straightforward. Now, there's other little, like parts and pieces to it. And like we'll start with the fuel inlet. That's just going to be how the fuel is connected. So, like whenever the one that we looked at, you had like a little fitting, that little brass fitting that comes off to the side. It's just going to hook up right up to the fuel line, and it's coming right into the fuel bowl. Then you have the mixture needle that's right there, which controls the discharge nozzle. That's going to help control how much fuel that discharge nozzle can get. So you might have to make little adjustments to try to help get the idle. So you'll set the engine at a certain setting, and you'll look for a certain level of RPMs, and then make sure it's not running rough or anything else like that. And then you have the air bleed, which allows the air to be mixed with fuel and drawn out of the discharge nozzle to decrease fuel density and promote fuel vaporization. And that's really kind of the big parts and pieces of the float type carburetor. Like I said, it's not really overly complicated or anything that's super crazy. It's pretty straightforward. Like I said, it just works just like the old cattle trough or even like your toilet. If you want to see how a float type carburetor looks like, pull the back of your toilet off and watch the float as the back of the toilet starts to fill up. The float will float it, and it'll come up to eventually it closes where the water comes in at, and then from there the water is just ready to go for the next flush. And then whenever it flushes, it'll draw all that water down into the bowl, and the process will start all over again. The float type carburetor is the same sort of technology, nothing that's super duper crazy. Where it will get people in trouble or become kind of a hassle is whenever you end up having to make the adjustments to things like the mixture needle or the idle and things like that. And there's procedures for that, but there's also at least some subjectivity to adjusting the idle and the mixture to make sure that make sure that the engine's running correctly, and you'll learn that just simply by making a lot of carb adjustments. That you'll reset it to like the factory settings, and then you'll have to adjust it here or there to get it just right per whatever the engineering calls for. All right, this is what the bowl on the inside actually looks like. You can see that it's not like I guess a typical bowl that you would think. It actually has, it's kind of like a half moon shape, or at least this particular one does. The one that we looked at earlier actually is a bowl in the kind of the more traditional sense. But essentially, this will fill up with fuel. And as this fills up with fuel, you can see the little inlet there where fuel can then go down into the metering jet off to the side or off in the center of the venturi there. That's a big circular area with that little probe looking thing that sticks out. That's going to be the carburetor jet. Now, the way that it does that is atmospheric pressure is going to push down on top of the fuel, so you have that steady 4.7 pounds, and then because the pressure is lower inside of the venturi, it's going to start to pull on that fuel. Or rather, I guess the right way to say it is that the atmospheric pressure on the inside of the bowl is greater than the atmospheric pressure on the inside of the venturi, which then causes a differential. It pushes the fuel down and then out the jet and into the venturi that way. That is basically how the bowl works. That's what it looks like. Okay, so let's talk about the air bleed a little bit. So all the air bleed is effectively doing is helping your carburetor run with the appropriate level of mixture at low idle speeds, with either more air or less air to make it richer or leaner. Now the air bleed screw will come in or come out, allowing more or less air into it, and so the more you screw it in, the smaller the orifice get, or the smaller the space for air to come in is at. So therefore, the richer it'll run, because you're putting more fuel in the line as opposed to the fuel air mixture. Whereas with the if you to open it way up and let a lot of air in, it's going to lean that mixture out. And so then this is primarily when you're just sitting at idle. Once you're running and gunning and you're at 2,500 RPMs and climbing, then this won't matter as much. But at idle, this is where the air bleed problems will particularly manifest. All right, and so let's talk about the idle system on it. Idle is pretty straightforward, pretty simple. It's just going to be kind of like a bypass to the main jet. Now, the reason why we would want to idle is we want the engine to run whenever we don't have power applied to the to the engine for, say, like climbing performance, stuff like that. We want to be able to pull it all the way, all the throttle all the way back, and still be able to idle a little bit. Now it'll be kind of like rough and clunky a little, a little bit, because it's not getting the full meal deal in terms of fuel that it needs. But we still want the engine to continue to run, to operate. And for flight operators, especially for like flight training, you're going to end up pulling the power to idle a lot to simulate different things, and you don't want to have to get into an unsafe situation where you're doing, let's say, like an emergency approach, and then you're just like, okay, like we've done all the things that we want to do, let's go around. You put the power back to it, and all of a sudden, man, you don't have it anymore, right? So the idle is really, really important, and all it really is a bypass. So you notice on this graphic here, you have the throttle plate, the little butterfly plate that's up at the very top. It's closed, so that way there shouldn't be any fuel coming from the main jet into the engine, but the engine still needs to operate, still needs to stay alive and stay running, so that way we can get the power back immediately without having to go through the restart procedure. And that the idle jet basically is like a little channel that comes on the backside of that throttle plate, and allows fuel to come in from behind the throttle plate and keep it running. That's all it really is. Now, if you have a engine that doesn't want to idle, idle's really rough. This is probably going to be where your problem is. A lot of times you get some trash in there, or if it's set up for a long time, the fuel, which has additives in it, if you remember from General, and those additives over time will settle to the bottom. Well, that's true in a fuel tank. You'll see the sludge on the bottom of the fuel tank. You have to kind of clean it out. But also, you'll see it whenever fuel evaporates, they'll leave that additive behind. Well, if this happens multiple times over a period of years, you could easily get into a situation where that gunk is just starting to like collect around that idle jet, and you'll start to see it to attract dust and dirt and anything else that might be in the air that's coming through there. Also, if you do a lot of off-airport landings, this is a thing that could get gunked up just from operating in the environment that it's in. So that is the idle system. Okay, so let's talk about the mixture. The mixture, just like we were talking about earlier, has to be adjusted per the altitude that you're operating at. And what that effectively will do is allow certain amounts of fuel to come into the jet. Now, keep in mind your carburetor needles, your air bleed needles, all that stuff, all the jets, everything is going to be kind of a steady state for ground operations, primarily set at idle, and then tested at max power. However, the mixture has to get adjusted as you climb in altitude. So the way that happens, there's a red handle inside of the cockpit that slides forward or backwards or in or out, depending on the style of handle that's there. That goes through a series of linkages that actually moves the needle in or out of the carburetor. Now that needle will open or close this little orifice that allows different amounts of fuel into the carburetor itself. Either opens up wide and lets a lot of fuel in to enrich the mixture, or B, you can cut off the engine by simply pulling the mixture handle back, and the engine will shut off totally. And then you can turn around and feather it one way or the other to get the maximum amount of RPMs that you need for an in particular uh, flight configuration at a certain altitude. So like my airplane on the ground, you do full rich. Once you get up to about 8,000 feet, you're going to have to start pulling the mixture back a little bit to pull some of that fuel back, so that way you can get the right RPMs, because you're trying to keep that one-to-one fuel mixture, just like we went over on the whiteboard a few minutes ago. But that is how the mixture works. Now, there's a few different types of additions that you can get into with carburetors. One of which is an accelerator pump. Now, an accelerator pump, basically what it will do is add just a little bit of extra fuel in case of a rapid, sudden opening of the throttle plate. Now, you could have a situation where you're flying along and you firewall it, and all of a sudden you need to go around, or something's happening that you need a lot of power all of a sudden, and the carburetor spitters and sputters because it can't catch up with the demand on it effectively. And so what the accelerator pump does, that in the event that happens, it basically just dumps fuel as much as it possibly can to allow for you to have that immediate power, and then allow the carburetor to kind of go through its thing to catch up naturally, so that way it keeps on flying. These are not on every single carburetor; they're kind of unique, and you'll see them as you start to work on them. But know that the main thing is to know that you could have a situation where a engine is causing some sort of problems, and the accelerator pump is going bad in the carburetor, and you have to get it fixed. All right, so another subsystem of a carburetor that you could get is an economizer. What that does is basically it enriches the fuel beyond about 60% throttle setting. So if you're max power going, you need as much fuel as you possibly can get, up to a certain point at least, to make sure the engine runs correctly. If you are below 60%, then some of that fuel you don't need because you're not generating as much heat, so you don't need the extra heat dissipation qualities of the fuel in the engine. And so if you lean the mixture back a little bit, you'll actually save a little bit of gas. So that's what the economizer does. Below 60%, it basically shuts that excess fuel off and doesn't let it get into the chamber. But above 60%, it enriches the fuel so that way you can have the max amount of fuel that you need, plus that extra little bit that you need to turn around and cool the sidewalls. As time went on, people realized, hey, look, we need a different type of carburetor in order to keep these planes flying. So they invented a pressure carburetor. Let's talk about the differences between a float type and a pressure type carburetor, and the things that we need to know about while we're doing maintenance. So as airplanes progressed, the pilots and the designers started asking more and more of the airplane, and so high-speed, high-G maneuvers became more of a status quo than it is kind of a rarity as it was with the old biplanes and whatnot. Well, one of the things that would end up happening is that as the airplane went inverted or went to a high-speed dive or had any sort of negative G whatsoever, the float would stick up, and then that would cut the fuel off. And as the fuel in the bowl of the carburetor was exhausted, the engine would start to sputter and die. And some of your instructors have actually even experienced this with doing these crazy dives on Cessna 172s, and I would encourage you to ask them about it because it can be somewhat terrifying. And the engine likely will restart once the fuel gets going in there, but in the context of a dogfight, you just can't afford that half second of loss of power, or else it could be it could mean your life. So therefore, they had to come up with some new apparatus to feed fuel to the aircraft, even whenever the airplane was upside down or was in some sort of high demand situation, and that's where we get the pressure carburetor. All right, now if we look at this cutaway, we start to understand that the pressure carburetor is very different than a regular downdraft carburetor. Now, the pressure carburetor uses a pump of different varieties to create a solid line of fuel from the carburetor to the engine. Now, the only thing the Venturi actually does here is it controls the quantity of fuel to the metering jet in proportion to the airflow to the engine. That's all they will. That's all it actually offers. Now, the injection carburetor is a hydromechanical device employed a closed feed system from the fuel pump to the discharge nozzle, meaning that there is no air gaps or anything like that. It's simply just a straight. We're going to spray fuel, and that's it. Now, this graphic represents a pressure type carburetor simplified so that it's only the basic parts shown. So keep in mind, if you go back and you look at the picture we just showed of the other pressure carburetor, it is a lot more complicated than what you're seeing here. And that's just simply for understanding's sake, because honestly, the pressure carb is fairly rare. Most of them are going to be downdraft carburetors, or we're going to have a fuel injection system. The pressure carb was kind of a stopgap between going from downdraft to fuel injection and on from then on. Anyways, so the pressure injection carburetor is an assembly of the following units: the throttle body, the automatic mixture control, and the regulator unit, and the fuel control unit. So there's four subcomponents of a pressure carburetor. So let's first talk about the throttle body. All right, the throttle body is pretty straightforward. It's all the things that you kind of think of whenever you think about a carburetor. It contains throttle valves, the venturi, a boost venturi, and impact tube. So all the air entering the cylinders have to flow through this throttle body, and so therefore it's controlled. It's the air control and the measuring devices. It's actually what's going to be what keeps the throttle or the engine running at the rate in which you want it to run. So whenever you set your throttle, you're actually moving the throttle plate down there, and then everything else is happening down trace of that control input. All right, next is the regulator unit. Now I'll tell you, and I'm not an expert at pressure carbs, but I do know this, is that if you have a pressure carb problem, it's 9 times out of 10 going to be in the diaphragms of these regulator units, because they'll turn around and they'll start to degrade over time, and you start having problems with just anything contact with fuel that can flex and is thin like that. It's just going to end up eventually kind of falling apart. Anyways, so the regulator unit's a diaphragm-controlled unit divided into 5 chambers, and it contains 2 regulator unit diaphragms and a poppet valve assembly. So chamber A that you see located on there, so it's going to be on the far left-hand side, just above that balanced diaphragm, or the line that goes across where the balanced diaphragm is. Chamber A is regulated to air inlet pressure from the air intake. Chamber B, so just to the right of that, is the boost venturi pressure. Chamber C contains a metered fuel pressure controlled by the discharge nozzle for a fuel feed valve. Chamber D contains an unmetered fuel pressure controlled by the opening of a poppet valve. Chamber E is a fuel pump pressure controlled by the fuel pump pressure relief valve. The poppet valve assembly is connected by a stem to the 2 main control diaphragms, and the purpose of the regulator unit is to regulate the fuel pressure to the inlet side of the metering jets in the fuel controlled unit. And the pressure is automatically regulated according to the mass airflow to the engine. So essentially, you set the throttle, the air comes in there, your airflow is then going to dictate what the fuel pressure should be to keep that 1-to-1 ratio, so the engine continues to run in accordance with best practices. Okay, so let's just kind of talk through how this could potentially work. All right. Now let's say that there's a given amount of pressure, amount of airflow that's going through the throttle body, and a negative pressure inside of chamber B. So let's say we got like 10 pounds of pressure going through the throttle body, and then negative pressure inside of chamber B. Call that, we'll say -1. All right. This tends to move the diaphragm assembly and the poppet valve in the direction of the open poppet valve, permitting more fuel to enter into chamber D. All right. So imagine that whole assembly starts to slide, and then it allows for chamber D to start kind of filling up. Then the pressure in chamber C is constant, and usually it's 5 psi. Sometimes it's 10, but 5 or 10 psi. It's held that way by the discharge nozzle or the impeller fuel feed valve. Now, therefore, the diaphragm assembly and the poppet valve moves in an open direction until the pressure at chamber D is 5 and say a quarter or so. Under these pressures, there's a balance condition of the diaphragm assembly with a pressure drop of a quarter psi across the jets and the fuel controlled unit, either auto riches or auto lanes. Now, if the nozzle pressure in chamber C rises above that 5 and a quarter, the diaphragm assembly balance is upset, and the diaphragm assembly moves to open the poppet valve to establish the necessary 5 3/4 pressure in chamber D. Thus, the quarter psi differential between C and D is reestablished, and the pressure drop across the meter and jets remains the same. So the end goal of all of this, even though it's kind of confusing the way that it works, is to make sure that the pressure to the fuel meter and jets remains the same. And what you have is that you have 4 different chambers of pressure that during different configurations will open and close to help that pressure equalize, and then it will cause an equal pressure to the fuel jets. Now, all right, so let's talk about the fuel control unit. The fuel control unit is attached to the regulator assembly and contains all the metering jets and valves. So this is basically all of the little intricate parts that could potentially get clogged or fail or whatever is going to be inside your fuel control unit on a pressure carb. Now, there's a set of valves that are actually in there: the idle needle valve, the power enrichment valve, the regulator fill valve, and the manual mixture control. All right, so the idle needle valve meters the fuel in the idle range only. So it's only a factor whenever the airplane is idling. So if you're troubleshooting an airplane that has a pressure carburetor on it and it's just like idle is really rough, there's a couple of different things that could affect it. But one of them is the idle needle valve is clogged or stuck open or not opening fully or whatever the thing may be. The manual mixture control is a rotary disc valve consisting of round stationary disc with ports leading from the auto lean jet to the auto rich jet and the two smaller vent holes. Now we're going to look at a graphic here in just a second to kind of go over that. So we'll table that one. The regulator fill valve is a small poppet valve located in the fuel passage, which supplies chamber C of the regulator unit with metered fuel pressure. So you remember the different diagrams. The regulator fill valve is one of the way that those diaphragms get filled. Now, let's go back to this mixture control rotary disc valve that we talked about a second ago. Now, the three positions of the manual mixture control lever make it possible to select a lean mixture, a rich mixture, or stop the fuel flow entirely. And the idle cutoff position is used for starting and stopping the engine. So during starting, fuel is supplied by the primer. So essentially, you have you have this disc that will allow for fuel to either flow or not to flow based on the mixture setting inside of the aircraft. And you can kind of see, like, here's the manual control valve plate that has different openings to allow the fuel to come in or get stopped based on its position, and its position is going to be dictated by the mixture knob inside of the cabin. It's either going to be set to full rich, auto lean, auto rich, or it's going to be just idle cut off altogether, which means that one of the solid parts of the plates is over the port. They're basically starving the engine of fuel. Now, for starting though, it'll be in the same place, but like you'll end up using the primer to fuel the engine, and then once it fires off, you'll put the mixture into the lean or rich configuration based on whatever the AFM tells you to. All right, so the last component that we want to look at is the automatic mixture control, and it consists of a bellows assembly, a carbureted needle, and a seat. And you can see it clearly right here, just above the throttle body. Now, the purpose of the AMC is to compensate for changes in air density due to temperature and altitude changes. So, what AMC effectively does is it auto leans your mixture as you go up. So instead of climbing up and then having to lean the mixture back and then lower the and then pull the mixture so that way it maintains that 1-to-1 ratio like we talked about before. The AMC will basically do it for you, and that's why you have like an auto lich, auto rein. This is the auto part of it. There's two basic settings, and you're going to set it these two different settings, and it's going to do all the leaning for you. So if you have a aircraft that has a pressure carburetor that's always too rich, always too lean, this basically will tell you exactly what's wrong with it, because there's really only one thing that could be wrong other than operator error. Alright, so whenever you put it all together, this is what it actually looks like. This is a Stromberg pressure carburetor. It's got it's a low pressure single barrel injection type carburetor. And so you can see the graphic that we looked at first, just to kind of understand, there's like 4 parts of it, and this is how a pressure carb works, is a lot simpler than it is whenever you have an actual cutaway of a real life pressure carburetor. Now look at the complexity of this. All the little channels, all the little valves, the diaphragms, the springs, all of that. And think about, like, if you were flying in, say, the South Pacific in like a P-47 and or something with a Wasp engine, and you do a dust landing. If you don't catch every bit of that dust and keep it out of all these channels, out of your fuel supply and everything else like that, just imagine the issues that you're going to end up having. look back in time and see like all of the crashes that have happened over the years, and wonder how many of them were from fuel starvations that maybe we don't even know about. And then this could potentially be why. Look how complicated this little piece of machinery is, and look how critical it is. So it didn't take very long for people to stop back and say, hey, maybe there's a better way of doing things, and that's where fuel injection comes in. Modern aircraft now that are just coming off the line are trending more and more towards fuel injection. So for performance sake, everybody wants a fuel injected engine. What is fuel injection? How is it different than carburation? And what should we know about it as airframe and power plant mechanics? All right, so here is a full-on fuel injection system. Oh, that's a tongue twister. All right, so if you kind of just look at it, you'll start to see some very similar, I guess, components with the pressure carburetor. There's a throttle body, just like you have on your carburetor, your pressure carburetor. You're going to have a fuel pressure indication in the cockpit, so that way you know how much fuel is actually going there. You're going to have a manifold valve assembly. That's a new one that's going to break up the fuel and send it to the different injectors in different places. And then you have a fuel control, which is similar to the other two as well. So let's take apart a couple of these components, and we'll put them together, and then we'll finish off by talking about what could potentially go wrong with a fuel injection system. Okay, so this is a cutaway view of the airflow measuring section. The airflow consumption of the engine is measured by the sensing impact pressure and venturi throat pressure in the throttle body. The pressures are vented to the two sides of the air diaphragm. Now this shows the measuring section, and the movement of the throttle valve causes a change in engine air consumption. This results in a change in the air velocity in the venturi. Now, when the airflow through the engine increases, the pressure on the left of the diaphragm is lowered due to the drop in pressure in the venturi throat. As a result, the diaphragm moves to the left, opening the ball valve, and contributing to this force is the impact pressure that is picked up by the impact tubes. So essentially, this is the mechanical sensing device that says, hey, look, the airflow is increasing, so therefore we're going to add a little bit more fuel pressure, or the airflow is decreasing, so we're going to pull it back to maintain that 1-to-1 ratio. So if you have a mixture problem with a fuel injection aircraft, it's very likely that this is going to be where the problem is at. All right, here's kind of a cross section of what you can expect to see on a airflow section of a fuel injected aircraft. You have air that comes in up to a regular throttle valve, just like you would anywhere else. There is an impact tube that has a fuel diaphragm, an air diaphragm. Everything is fairly consistent that we've seen before at this point. The airflow section is essentially just the big throttle body that is going to turn around and allow the air to be atomized, or the fuel to be atomized in the air, and the air to be metered, so that way it responds appropriately to the throttle settings from the cockpit. Okay, the next component in line is going to be our regulator section. It consists of a fuel diaphragm, like the one that you see here, that opposes the air metering force. So fuel inlet pressure is applied to one side of the fuel diaphragm, and metered fuel pressure is applied to the other side. The differential pressure across the fuel diaphragm is called the fuel metering force. Now, the fuel pressure shown on the ball side of the fuel diaphragm is the pressure after the fuel has passed through the fuel strainer and the manual mixture control rotary plate, and is referred to as the metered fuel pressure. So fuel inlet pressure is applied at the opposite side of the fuel diaphragm. The ball valve attached to the fuel diaphragm controls the orifice opening and the fuel flow through the forces that are placed on it. The distance the ball valve opens is determined by the difference between the pressures acting on the diaphragm. Now, this difference in pressure is proportional to the airflow through the injector, and thus the volume of airflow determines the rate of fuel flow. Okay, the next is going to be the fuel metering section. So the fuel metering section is attached to the air metering section and contains a inlet fuel strainer, a manual mixture control valve, an idle valve, and a metering jet. So this is going to replace a lot of the fuel metering components that you've seen in the pressure carb and the other carburetor, but it's going to accomplish the same thing. It's going to change the settings on the different jets to allow for different modes of operation, if you will. The idle valve is connected to the throttle valve by means of an external adjustable link, and in some injector models, a power enrichment jet is also located in this section, and the purpose of the fuel metering section is to meter and to control the fuel flow to the valve divider. The manual mixture control valve produces a full rich condition when the lever is against the stop, and progressively a leaner mixture as the lever is moved toward the idle cutoff. Both the idle speed and the idle mixture may be adjusted externally to meet individual engine requirements. All right, this is what one looks like in real life. You can see the cutaway there. So well, you can see the fuel inlet metering. So it's basically the same thing as the graphic that we just looked at. You can just simply see the springs and all the inner workings in there. Generally speaking, these are going to be fairly reliable. They're enclosed units and things, but you can still see if there was trash in your fuel, it's going to get in there and cause a bunch of problems. So it's another thing to think about. If you have an engine that's sputtering, it could be any number of these things. All right, so once we have our fuel, properly metered and it's headed to the cylinder, it's ready to get fired. The first thing it's going to hit is this spidery-looking device on top of the engine cylinders. That's then going to divide it and send it out to the individual fuel injector nozzles. You have what's called the fuel divider, or the manifold valve assembly, if you want to be super proper about it. But essentially, all it is a manifold that has different little ports into it that will then allow the fuel to go to the different places that it needs to go for it to fire. Now, the whenever you go to do an annual, you're going to pull all these guys out to include the fuel nozzles. You'll clean them out, let them soak, probably some isopropyl or whatever, blow them out with shop air, so that way you can be sure there's no contaminants in the line or anything. Because over time, especially if the engine sits for any length of time, it could gum up the insides and restrict the fuel flow. Okay, so this is what one looks like in real life. These will typically be mounted on top of the engine, and you'll have little stainless steel lines that will go off to the individual injectors at every cylinder. There's also typically a return line that will go there, as well as a supply line as well. So if you have like a 6-cylinder engine, you're likely going to have at least say 8 of these little guys that will spider out and go to different places. Okay, so this is the end of the line for your fuel, is the fuel nozzle assembly that's going to come at the very end of it, and this is what actually is going to finally atomize the fuel and spray it into the cylinder. Now these will get, like I said, pulled off every annual and cleaned. The big thing with these is that they are typically very, very, very soft, and so you don't want to tear them up. They are also expensive to replace. And basically, if you don't have all of them in good working condition, that engine is deadlined. And so you want to, whenever you go to take these things off, be really, really careful not to damage them, and then also be very, very careful not to lose them. But ultimately, all there are is a little bitty brass nozzle that has ports in it to allow the fuel to get pressurized inside of it, squeezed, and then pushed out those little ports, so that way it can mix properly with the air to cause combustion. Okay, here's a couple of different types that you could come across. There's the standard one that's on the far left-hand side. You notice that there's like a little air screen, and then there's a shroud that go over the screen. The screen is generally what will get clogged up, and you're end up having to clean out. And then you have the 550 series, the Crossflow IO 360 that you'll have, and then a turbocharged nozzle as well, which looks totally different. However, they're all going to be somewhat unique to the engine that you're going to be working on. It's important to make sure that you use the right one for the right engine, and also be very, very gentle with them, because these things can get messed up. That screen gets broken, or you have like loose strands on it, or if you end up dropping it on the ground and dinging the threads or whatever, that's an expensive mistake. So you always want to be very, very, very gentle with them.